Hi everyone, welcome to another episode of Mr. Carlson's Lab. Today I have a special treat for you. We are going to design a power supply together out of junk box parts. So it's just going to be parts and pieces I have laying around here. New parts, old parts, just probably even some parts from the 40s. So we're going to be using all of these parts to design a power supply that will be better than the factory power supply that this radio receiver came with. And to boot, it's going to be regulated with vacuum tubes. So we'll design a power supply and a vacuum tube regulation system and all of that great stuff in this video. And I will take you through my entire thought process as I'm doing this. So let's get started. If you're new to my channel, let me start by saying welcome. And if you're not up to speed with the previous video, just say you're joining in now, I'll quickly bring you up to speed with what's going on with this radio receiver. So first of all, this radio receiver used to fly around in a B-17. So the radio operator used to use this thing in an old warbird to intercept signals. So they're really, really great receivers. These radio receivers used to run on 28 volts DC, and they had a dynamotor inside them that was very, very noisy. So what a dynamotor is usually a motor about, as big as a large potato that used to sit in this area right over here. And what they would do is they would take the 28 volts DC fed to this radio receiver and step it up to about 210 volts for the rest of the radio receiver because vacuum tubes take an elevated voltage to operate. Now, it was very common way back when. Nobody wanted to listen to a whirring dynamotor, let alone did they have a 28 volt DC supply in their home. So what they would do is they would take the dynamotor out and build another power supply that would run off of 120 or 115 or whatever they had way back when. And that would be nice and silent. And that's what's done in this radio receiver. And it's done in the majority of these radio receivers that you find. Everyone almost pulled out those dynamotors because nobody really wants to listen to that whirring noise, let alone the smell of the commutators and of course, the hot oil and everything like that. So, it's pretty common for people who want a nice silent radio room, especially when you're listening to distant signals, right? So we found in the previous episode that the person that built this power supply did a really nice job, but the voltage that it's supplying is a little low for the radio receiver. We want to restore this radio receiver and make it perform the way it performed when it rolled off the factory line minus the noise, basically. So what we're going to do is take this power supply out and scratch build another power supply that's going to supply this radio exactly what it needs or very, very close to, so that we can get the most accurate representation of the way this radio performed, again, when it rolled off the factory line. Now, before we do that, what we need to do is we need to see what this supply is actually supplying to the radio receiver. So, for example, this was, common in the 40s. This has been through a lot of radio operators' hands or just hobbyists' hands throughout time. And what they do is they've done all sorts of different modifications to these things. I've seen these radios so drilled with holes and there's switches added all over the place. This is the nicest representation of one that I could actually find locally, and that's the reason that we're going to do this one right here. It is relatively clean inside, looks really nice, and of course it's got some scratches here and there, but not too bad. So what happens is people rewire these things to make them operate at different voltages, and there's all sorts. There's just you could basically write a book about how many modifications there are for BC-348s. So just before we start to build the power supply, we don't want to create any more work for ourselves or build a power supply that's not going to work with the way somebody has modified this if we can leave it alone. So we're going to take some voltage and current measurements just before we start building that power supply. Then I'm going to go dig through my junk box with you. I'll show you how I'm going to do that. Pull out some just parts and pieces, and we'll throw a power supply together that will be better than the factory dynamotor, and of course better than the supply that's in here right now. In fact, it'll be very stable. It should be really nice for listening to CW or just distant stations. So I'll get a meter ready, and I get everything all turned upside down and powered up, and we'll see what the previous owner or owners have actually done with this thing right here, figure out what was going on in their mind when they put this thing together, and get started on that new power supply. One of the very first things that I noticed when I turned this radio over was the computer line cord. So the computer line cord, which is fine to use, is running directly into the windings of this transformer. There's no switch. So as soon as you plug this radio receiver in, this transformer is on, Whether you turn the switch on the front of the radio on or off, this transformer is always on. Another thing that's kind of interesting, I'll grab a pointer here, is you can see this black lead right here. So that's attached to the neutral side here, is running into this transformer over here. And then from the hot side of the line cord, which is attached to this transformer, we also have another black lead. You can see it moving down in here, right? So you can wiggle that around, right? That's running into this transformer over here. So what that tells me is both of these transformers are power transformers. And on top of that, they're both attached to the AC line and they both stay on. Now, we measured the B plus here the last time on these caps. So we know that the B plus is there. So the way that the power transformers are coded with their, this is very common for basically all transformers of this era and even some nowadays, is the color black. So when you see two black wires coming out of a transformer, it's most commonly the AC line, or black and white. When you see red wires, they're commonly the B plus leads coming out. And if you see a red and yellow striped wire, like you see down here, that is the center tap. So that's this lead right here, if I can get that. That right there is the center tap. That's very common for transformer wiring way back when. The filament winding that comes out of these transformers is a green colored wire. Now, you'll notice, you'll see over here, when I move this wire around, a piece of heat shrink tubing. So I pull the wire out, and it's capped off. So the filament lead that's coming out of this transformer, the filament winding in this is not being used at all. Kind of interesting. Now, something else that's very interesting is you'll notice over here, it says pin 4 is 6 volts. So have they converted the 28 volt DC filaments to 6 volts? We need to find that out. Why do we have a second power transformer? What is this supplying? So what I'll do is I'll get a meter in here first of all, and let's see what they're doing. So I'll back this out a little bit here, put the meter up here. Might be a little bit easier to see. Put that on to AC, turn this on. That looks okay. And we'll put this to the chassis, that'll work. I'll turn on the variac and isolation transformer. It's a current limited supply. And it'd be nice to actually have that somewhere where it's not directly in the middle of what I'm trying to do here, right? And maybe I will put a clip on that and make that just a little bit easier to get out of the way. Here, I'll just poke this into this clip here. Hopefully that is going to do the job. It looks like it is. I'll just clip that to the chassis over here. Get that out of the way so we can see what's going on here a little better. Okay, so it says pin 4 is 6 volts. Let's take a look here. They're numbered. There's numbers along here. So this top pin is pin 4. Okay. And look at that. We have 6.6 volts, which would be the heater voltage. Kind of interesting. So let's see on an actual tube socket down in here. I'll zoom on in. So this is the tube socket down in here, an octal tube socket. If we have that voltage here and then maybe an adjacent tube socket, because normally these are hooked in kind of a series parallel arrangement when you have the 28 volts DC going here. So most commonly, it's very easy to remember with octal tube sockets, is pin 2 and pin 7 are the filaments, or pin 7 and pin 8 are the filaments. That's most common. So just by looking at the way things are wired, you can usually very quickly tell. So I see that pin 7 is running to the chassis. Pin 8 is running off to one of the transformers over here, to this transformer. So it's not going to be 7 and 8. So it's going to be 7 and 2. So there we go. So we know that we have pin 7 is a chassis, so pin 2 is going to be the filament on this tube, and we should have roughly the same voltage up here, and there it is, 6.4. So we're dealing with a bit of drop through the line in here. So 6.4, so if we were going to go to an adjacent tube and see what's going on there, let's see, where does this one go? Looks like this one here, maybe pin 7 and pin 8. Kind of hard to see. So this is, yeah, so pin 2 of this one here is definitely not the filament supply. So it's going to be pin 7 and pin 8. So let's see if we get anything down in here. I don't know, depending on which way they've wired it, whether pin 7 or pin 8 is the filament. There it is. So they've changed this over. They've changed this whole thing over to a 6.3 volt filament system, which is absolutely fine because it makes looking for a power transformer for this much, much easier. So with the filament transformer being capped off, they must be using this as a filament transformer, which is very strange. So maybe the filament winding in here is different. So what I'll do is I'll remove this. There it is. It's folded over nicely. So the other green, well, I'll just shut this off for a moment. I'm going to poke around in here, and there's B+ in here, so I don't want to feel that. So where's the other green lead going? So they've tied the green lead in here to the chassis, so I'll zoom you in. So they've tied the other green lead here. You can see it, it's tied right here, and this is where they've bolted the tie strip to the chassis. So that's the other green lead there. So this one here, from the chassis, we should get a reading. So let's see what's on this particular wire right here. So maybe I should strip just a little bit of the end of that off. I will grab a wire stripper right here, something that'll make quick and easy work of this. Put that in there like so. That looks good. There we go. So let's see what this is going to read. So I don't want to hold on to this just in case they've done something crazy and it isn't a filament lead, and say somebody has wired this transformer in a different way. You never trust the color codes. It just helps give you a guide to what's going on. So I'll poke my lead into this here, and let's see what we get. So down there, hopefully that's going to read. Okay, so I'll turn the supply back on again. I've got this lead attached in here. Let's see what we get on the top. So the 7 volts there, so that is a 6.3 volt winding. That's just because it's unloaded. So this is obviously the filament transformer, because we don't have a filament winding here. So if we look here, so I'll zoom back in. So if we look here, we can see that we have an orange wire running up through here over, and it ends up right at the same pin that we measured the 6.3 volts at. So what's happening is they are running a separate filament transformer at 6.3 volts. So maybe the previous owner figured that this transformer didn't have enough current to supply the filaments in this. So they used a separate filament transformer to be safe. So that would be my guess. That would be the only logical guess, that they capped off. Maybe the transformer isn't rated to supply what this needs when the filaments are all in parallel, not series anymore. So what I'll do is I'll just fold this back up. That is only, you know, some pretty low voltage, and that's not going to stay on there, right? So I just don't want to have this touch anything in the way. Maybe I'll just cut that off again. And we'll just keep that out of the way. There we go. So that's just safer like that, so I don't short anything out with that. Fold it back over. Will this fit back on is the question. It does. There we go. So just leave it like that for now. So we know that the B+ in here was low. It should be about 210 volts. So this is where the B+ is. That runs out to the actual radio. And it's at 186. So I'll just zoom that out so you can see that 187. So that's really low. So that should be at 210 continually, or even just a touch higher. The radio's rated at 210. If you have one of these radios and you have it supplied at 215 or even 220, don't worry about it. This isn't a solid state device. It's not that picky. So 210 is what they spec'd for this. I would like to get as close to 210 as possible, but again, don't get too crazy over that. So you know, it's very easy with a solid state supply to set something wherever you want. So if you want something at 210, you can adjust the supply to give you exactly 210.00. But we're going to be using vacuum tubes because the power supply that we are going to make for this is going to be era specific. So I want the power supply that we're going to build to basically match what's going on with this radio receiver. I want to use the same era of tubes and maybe even if we're lucky, the same era of transformer. Wouldn't that be neat? So it just depends on what I got in my junk bin, so we'll find that out together. So this is definitely an extra filament transformer here. So you can see the orange lead from this. I'll put this back on AC here again so you can actually read it. So you can see it's 6.7 there, right? And that runs up to this pin right here. The orange lead is running up to the pin. So it runs right, that orange lead, you can see that's running from here, runs right back and right up to this top pin. It's curled around right there and soldered right where you see it there. So kind of an interesting situation. Two transformers, basically, as I say, I guess because this one here couldn't supply the filament, so they probably just tacked in another transformer to keep things a little bit cooler, is my guess. So we know that we don't need a 28 volt filament transformer. See, that was very important that we check this, because if I would have built a 28 volt a transformer system for this power supply and then found out in the end after I put the whole thing together that they had already rewired it for 6, that would have been a lot of work basically wasted. So it's good that we definitely checked that. Very important. Now let's check to see how much filament current this is actually pulling. So what I'll do here is I'll just shut this down. Want to take any guesses just as to how much filament current this thing is drawing at 6 volts? So you know what, at about 28 volts DC, we have about 1 amp or close to in the filament current area, being drawn in the filament current area. So what I need to do is, this is off right now, by the way, and powered down. So what I'll do is I'll put this meter onto the 20 amp setting, and we'll just clip this around the filament lead and find out. How does that sound? Hopefully I can display this to you. Maybe if I turn this around the other way. There it is. Okay. So let's see how many amps this is going to draw. Let's go. There we go. So we started out, because the filaments were cold, at about 4 amps. So we can see at 6 volts we're drawing about 3 amps. It might go just a little bit below once everything warms up. So we would definitely want safely a transformer that could supply a continuous 3 amps without getting very warm. And I can see now why they would probably have capped this off, because the B plus draw on this plus 3 amps on the filament is quite a bit for this little transformer down here. So that's probably the reason that they've done that. That's 3 amps right on the button. So there we go. So 3 amps of current draw. So I'll shut this down. And I'll remove this here. And let's see how much B plus this is drawing. See how much current this is drawing on the B plus line. The B plus line is right here. So we will go to one of the, let's actually take the center tap if we can and put it around the center tap here, and that'll give us a nice good representation. How's about that? Because this, when you use an amp clamp like this, this is designed for looking at AC. So we'll put that around here and put that down to the 2 amp setting. Let's see how much current this is drawing at on the B plus. So here we go. So you gotta wait till everything warms up, till the tubes start drawing current there. Hopefully you can see that okay. Move the focus onto that. So we're drawing about, that's 0.07 of an amp, so that would be 70 milliamps. So 71 milliamps. So that's about what this radio receiver is spec'd for. So it's not doing too bad. So that's right in line with everything that's going on here. So we know that we need a B plus supply that is going to supply, I would say, at least 100 plus milliamps, because we're going to have regulation going on. And we need about 3 amps of filament current. So I'll get a piece of paper and I'll draw up what we should actually be looking for, and how I plan on building this supply, and we'll see how close I come in. All right, so I'll shut this down, and yeah, I'll get a piece of paper and I'll quickly draw up a schematic of what we're going to do to replace this supply here. All right, let's design a power supply. Running off a generator power right now. We've got a pretty big power outage going on right here. So the noise that you hear in the background, you may hear the generator. That's not ours. That's an adjacent property. So the generator that's running here is very silent. Can't even hear it over here. So first of all, we want to build this power supply the way it would look back in the 1940s or the 1950s. So we want to build this the way, say, a ham radio operator would have built this way back when. So just to keep it era specific and everything, so no solid state diodes or anything like that. So we need a power transformer. It's the first thing we need. We're going to obviously need a primary winding. That's going to be at 120. And since we want to have vacuum tube rectification, chances are we're going to use a 5R4, maybe a 5U4 or something like that. So we need a 5-volt winding. We need our B plus winding. And because we need to light the tubes in the radio, we also need a 6.3 volt winding. So that's basically what we're looking at, a transformer with 4 windings in it. All right, any more that we find in the transformer is just a bonus, I guess. So this is going to be a full wave rectifier, or rectification setup. So we're not going to need any more than 1 rectifier tube. So run out like so. And we'll make this directly heated, right? Because we have our 5-volt winding here. And so this heats the tube, and we have our DC present right here. You're probably saying, well, aren't you going to have AC present with this winding attached? This is like an isolation transformer. So whenever you see vacuum tube circuits, any vacuum tube rectifier circuit like this that has a 5.3 volt winding that's attached to the transformer like this, you're saying, well, how can the DC be here without that 5 volts AC? There's no circuit. So this is just attached to the filaments alone. There is no lead out from this circuit at all. So there is no AC present from this. That's how that works. So you can look at this like an isolation transformer for the filaments right there. So since we are building this like something from way back when, we're going to need a filter reactor in here as well, like so. So 5 to 10 henries should be fine. So we'll say 5 to 10 henries, whatever we find, something in that range. This is the B plus winding is yet to be known, so we'll have to experiment with that. I'm going to look for a transformer out of an old radio receiver, and that should probably be okay. Now, the ground on this is lifted by an inductor inside the actual BC-348. It's in the transformer housing, and that's how we get our negative voltage for the 6K6, which it's supposed to have a 6K6 in it. I believe this is a 6V6 in it, but it's supposed to have a 6K6 in it. And that gives us our negative grid voltage for that tube. All right, so inside the radio, there's an inductor, like so, that goes to the radio's chassis or ground. And there's 15 volts across this. So this actually looks positive to this point because this is lifted. The actual center tap over here is lifted by about 15 or 20 volts usually, okay, in the BC-348. So we're also going to want some form of regulation. We want to keep this right at 210. So I'm hoping that this is going to be about 15 volts because it just works out that 2 regulator tubes are going to give us 225. So for example, I'll go up here. This is our resistor. For our shunt regulation system, we'll have 2 regulator tubes, so 3 tubes in total. So this should look pretty good, this power supply, right? Because it's about looks as well, right? It needs to look good. So we'll have another one here, and then this will run to this point right here. So this would be the supply right here, okay? So now, in order to get 225 across this to here, we need a 150 volt regulator and a 75 volt regulator. And it just so happens that they make them in that. So this is a 0A3 and this is a 0D3. Nice thing about 0A3s is they glow orange and these glow blue, so it's going to be pretty colorful as well. So these are gas type regulators. They're basically gas type Zener diodes or Zener diodes. So we want 225 here, right? The radio itself, measured from ground, we want 210 volts. That's in the specs for this particular radio receiver. I'll grab a schematic and show that to you here in just a little bit. So if we have 15 volts across this, right? So this here would be negative 15 volts to this point here. From point A to point B, we're going to have 210 volts. That's what we want. So from ground to this point here, that's what we're going to have, right? Because this is carried to the ground through this inductor here, and then this runs off to the negative bias actually for the 6K6. Now, if one of these tubes ever fails, we want to make sure if the power supply is disconnected from the radio that we can discharge these caps. We don't want these caps sitting here holding a charge. And we also want a resistor here, like so, to limit the surge voltage, because until the actual radio itself starts to come into emission, what's going to happen is the voltage at this point here is going to go very high. Right? So, and that all depends on the impedance of the actual power transformer itself. But I'll get into that later on. So what's going to happen here is this tube here will come into emission because it's directly heated. So the filament itself is the cathode. Within about 3 seconds, that'll come into emission. Since all the vacuum tubes in the radio receiver are indirectly heated, that means that the actual cathode has to be heated by a filament that's in the center of it. What that means is that the radio itself will take about 13 seconds in order to come into emission. So between this and that, you could say roughly 10 seconds we have a pretty high surge voltage across both of these. This resistor here will help to clamp that down a little bit and keep it realistic for these caps. So I'll probably just use 450 volt caps anyways, no matter what this is. So because I just have so many of them, and you know, they're so incredibly common. So we want to keep this surge below 450 volts just in case this winding will bring us up there, depending on the transformer that we find, right? So now, if you were to just run a speaker with this radio receiver, you could get away with some pretty low values of capacitance because we have an inductor here, reactor, that's doing a lot of the work, you know, helping us remove any of the ripple, okay? So since this radio runs on, or will run headphones, basically you're having 2 speakers strapped to your head, right? Or 2 crystal elements, whatever you want to use, right? What's going to end up happening is we're going to need some pretty good filtering to keep the hum down. So I would say, like, normally if you just had a speaker, this could probably be 4.7 mics and this could probably be 12, all right? And you would be fine with a normal speaker if you just wanted to run a speaker on this. But you say you're tempted to run a headset into the radio receiver, right? You're going to want this to be no lower than 22 mics, and you're going to want this to be no lower than 47 mics. How do I know this? Lots of power supply building. So in the past, I've designed so many vacuum tube power supplies and solid state supplies. I've done a lot. Let's just put it that way. So So 22 mics here with a 5 to 10 Henry choke and 47 should keep it down low enough. Now with the BC-348, there's always going to be, just a touch of hum just because of the circuitry. It's point-to-point wiring, and of course maybe even the filaments may induce a little bit of hum. So it'll keep it low enough that it wouldn't bother you with a touch of volume and a headset on. So I would say lowest 22, and 22 is a low enough value that you're not going to hurt the cathode inside the 5U4 or the 5R4. If you start to get too excessive with the capacitance here, it could actually damage the cathode of the tube. All right. Now I've done experiments that kind of say different, but to keep it within RCA or Sylvania or whatever their actual vacuum tube design specs, you want to keep this pretty low. I think that would be the best thing to do. So keep it at no higher than 22, and a 47 should be fine over here. This value will have to be determined depending on the actual what we get out of the winding here and what we get out of the rectifier. So we'll have to figure this out later on. This here could be 100K, and at a wattage that's going to be able to deal with the surge. And of course, if these two tubes here are in place and they haven't failed, this will clamp the circuit all the time. But if one of these tubes was to go to air, or one of these was to just fail, and this wasn't attached to the radio or anything like that, what would end up happening is this could go high for a very long time. So you want to make sure that this resistor can deal with that if, say, the radio was not monitored. I will most likely put this on an external chassis of some sort and plug it into the radio. So there will be an umbilical cord to the radio, which is absolutely fine. That will get that power supply out of the radio, get the heat generating out of the radio. And we can also use that for future modifications, that area that we leave inside the radio receiver. So a lot of people like to add product detectors for easy sideband listening. I'll probably design a product detector circuit for this radio receiver down the road after we've done the comparison, because then we can have fun with these radio receivers, and I'll share that process with you as well. So there's a lot of little neat modifications that you can add to this that just really will make the receiver very nice to use nowadays. So if I go about doing that, you can let me know in the comments below if you want to see me go very far with this particular radio receiver. There's so many things that we can do to this to make it really neat and still keep it kind of era specific. We'll do it all with vacuum tubes and all that stuff, no solid state stuff. We'll keep this all like the way a ham radio operator would have modified this way back in the day. So it should be a lot of fun. I'm looking forward to this. So this is what we're up against here. So I don't know what I've got for this transformer, and I don't know what I've got for this. So we have to look for two transformers, or a transformer and a reactor. So we'll have to go look for those, and we'll have to do some measurements and see what we come up with so that we can figure out all the rest of this. So I think we're well on our way. So let's go find a transformer here, and let's go find a reactor first, and we'll work with that and then build our way out and see what we come up with and build this true ham operator style. Here are some of the inductors and transformers that have managed to make it over here. There's still quite a few of these at the old place still, but some time back I moved a bunch of these. So I knew that we would be doing some projects together, so I wanted to get some of the lighter iron, if you want to put it that way, over here. So let's look for a transformer and an inductor. So some of these I've already, looks like I've tried in the past for other projects. Looks like a full wave rectification setup here with a filter cap on it. Nice heavy transformer. Hammond, and this one is short on one winding, so there's no standard filament winding. So it has a rectifier filament winding, the B+ side, and then this is all primary voltage taps here, so you can compensate for a pretty bad supply, it looks like. So yeah, we're short on one winding, so that won't work. Core size on this one's a little too small. Again, we want to plan ahead too, right? So after we've done with the comparison, comparing all the receivers together, we can have some fun with these things. As I say, maybe add a product detector to this, to the BC-348, maybe make a little bit better of an audio section or something like that in there. So, we can do that with other receivers as well. We can, have some fun with it once we've done the comparison, right? Of course, keeping everything era specific, kind of like we're doing right now, right? We don't want any solid state components in any of these receivers. We want to keep everything kind of the way it would have been done way back when. And we kind of want to build this ham operator style as well, right? So we'll be doing some experimentation and stuff like that. So it should be a lot of fun. Anyways, yeah, some pre-built chassis. As you can see, there's some pre-built chassis in the back there as well. This transformer looks like it could possibly do it, but it is a little light on the iron side. Again, for modifications down the road, I don't think I'd want to go with that. And this is kind of a, looks like it has a nice, filter reactor here, or choke. So probably a little small though. So again, we want about 100 milliamps or so, and maybe a little extra would be just fine, right? So this is all just, some of these I've marked, as you can see here in the past. This looks like audio interstage. I remember this being a filament transformer for some 866 rectifier tubes. This here looks like it's out of an old radio, and it's got about the right size of a core. Nice looking case on it. So with paint, that would look really nice. So what do we got for windings here? So we've got probably a winding here. The wires look the same. It was really common back in the day in these old radios, especially Rogers and DeForest Crosley and things like that, for them to use this type of a tape. Usually it was on the primary side, but I'm seeing it all over the place here. So we have a winding here, looks like. A winding here. A winding here because the leads are twisted together. Sometime in the past, I may have pulled this out of somebody else's project or something like that. So another winding. Looks like it has about the right amount of windings. So this might be a very good candidate. So let's take this one, use that as a try. If it works, it works. If it doesn't, we'll be back here trying some more. Look at the core size on that transformer back there. Look at that. It's like this. Will that operate down to 10 cycles or something like that? It's probably a 25 cycle transformer. Even for 25 cycles, that's a little excessive. Look at the size of the core on that. That's just crazy. Again, for inductors, again, I've got some here that have got some numbers marked on them. So DC resistance, obviously. This is kind of an open style. I don't know if I want an open style because this is going to be on top of a chassis, right? Nice painted up chassis with kind of an open concept. So I guess I'll stay away from the open style here. Let's see if anything else just kind of, I'm looking for 2 leads. That's how I'm looking for an inductor here. So anything with 2 leads sticking out would be an inductor reactor of some sort. So this one back here, maybe. That's got 2 leads. That's looking pretty nice. It looks like the same type of design as this one here, right? It's got the slope kind of on the bells. See that? The slope there? Right? So they look like they would work together. And that would look good, side by side on a chassis. Something like that, right? So, yeah, the same kind of mounting and everything. So that looks, these would work really nice together. So hopefully this has the right amount of inductance. It's about the right core size. That should deal with 100 milliamps. And yeah, they look really nice. All right, well, let's give these 2 a try. Let's go make some tests on these things and see if we have any success. Okay, let's see what we've got going on here. Put that on there. Let's see. So what we want to do is just verify windings first, right? I would have marked these normally if I had experimented with this before. So there's somewhere closer. Hopefully you can see that okay. So let's see what looks to be the primary here. Again, the tape kind of gives it away, and the wires are the same, so it's probably a winding of some sort. Which it is, 8 ohms. So let's see if this is attached to any other winding. It is not. It is not. It is not. Those readings you see are me holding this right up in the mega ohms. So, nothing there. And here, yeah, nothing. So these 2 are obviously a winding. I'm thinking this is most likely going to be the primary. So it's easy to identify. So we know that this is, what's about 8 ohms or something like that. connection there. Yeah, 8 ohms, something like that. Close enough. So if this is the B+, these are red leads, we're going to have some pretty high resistance compared to the other one. Get that out of there. Oh yeah, I would say 295. So that would be from red lead to red lead. So we should have roughly half, close to, if that's the center tap. 153 and 142. Yeah, so that's the center tap for this winding. So that makes sense. That's why these are wrapped like that. So this is going to be the B+ winding. So we got these two twisted together, obviously a winding. That's going to be obviously a filament winding. That's really low resistance. Is this a center tap? It is. So whether this is for the rectifier, sometimes they, in the B+ section, they have a center tap on the actual rectifier filament and that leads out. So this could be either the 6-volt winding for the regular filaments, or this could be the 5-volt winding. We'll have to determine that once the transformer is powered up. And we have another winding here. If I can get some form of a connection on this. Do we have a... Yeah, we do. There it is. Squeezing the leads here. So the next thing to do is power this up. So I will attach this to my isolation transformer and current limited variac supply, and by no means am I going to be testing this the same way I just did, because this will be supplying current at that point. All right, I have my isolation transformer and current limited variac supply set up. Now, I'm going to be testing this transformer. Don't try this, let me do the dangerous stuff, okay? So I've got a lot of experience at this. I've been doing this stuff for years, and I know what I'm up against here. Very, I would say very familiar with this process. So if you want to learn more about this kind of stuff, and of course, if you're interested in experimenting with transformers, what I'm doing is very common, but it's not seen all that much today because, of course, it's kind of a specialized thing when you're dealing with B+ voltages and things like that. So you can learn more about this in my electronics course, or you can read about it in books and do all that kind of stuff, whatever you're into. I talk more about this stuff there. Again, I teach a lot of older knowledge there, stuff that isn't really talked about nowadays. So yeah, if you're into that kind of stuff, a lot of this stuff is on Patreon in my electronics course. All right, so let me do the dangerous stuff. You just watch. So what I'm going to do is attach my isolation transformer and current limited variac supply to the primary, or what I think is the primary at any rate. So the first thing we'll do is we'll test the B+ winding. Now again, we want to go from the center tap to one end. Okay, we don't want to really just right off start going right from end to end, because we don't know what the transformer is going to put out. So this way we know that we're going to get half of what this is end to end, and then we can mark this down. So I'll get a piece of paper here so we can kind of remember what's going on in this transformer here. So I'll just quickly scribble this up here, and we'll start with the B+ winding. Just like that. We have a filament winding here and another winding here. I know there's a center tap on one of them. I don't know which one it is. And this is the primary. We know what we're doing here, right? So hopefully this is on this winding. If it's on another one, we'll find out. So I'm going to turn on my isolation transformer and current limited variac supply and measure this here and see what we get. So before we do anything, let's just hook the meter up, get some light going so you can see what's going on. This isn't on right now, obviously, so I don't want to be anywhere near those while they're on. Everything is turned down anyway, so the voltage is going to be relatively low right now. Okay, so here we go. It's current limited. So that's with the variac pretty much completely off. So we have 3 volts. So now if I turn this up slowly and watch the bulbs on the variac, so if you can see up here, I'm watching these bulbs right here. If I turn this right up, if we have a problem, those would glow bright. And that's about right. So there is no problem. So that's obviously the primary. And the primary from the center tap right, to one end is we're getting 267, and that's AC. So now if I was to bridge the bulbs out, so what I'm going to do is there will be no current limiting now. We don't need it because we know everything's fine. So if I bridge the bulbs out, so now it's just directly applied. There's 330 there. So 330 from one end to here. So we know there'd be 660 from end to end. Now keep in mind, this is a small transformer. You know, you hear a lot of 660 mentioned in, you know, the industrial world and things like that. That's just the way this is wound. This has nothing to do with that at all. So that's really good. So I've shut everything off here. You can see everything's down, and that's good. So we know that we've got 330 and 330. That's very nice. So we can work with this. So far we're doing very well. And I can't see anything else going wrong after this. So let's test this winding here. So we know that this one here is going to be low ohm, so we know this is going to be lower voltage. So let's go end to end, and we know that this is the center tap for that winding. So here we go. So that'll be the 6-volt winding. Interesting. So it has a center tapped filament winding, just a standard filament winding, which is kind of nice. So it would be good for an amplifier. So what we'll do is on the piece of paper here, I'll just draw the center tap to here. So this is the filament winding here. So we've got, it's 7 volts, but under load again, it would be 6. So we have our 7 volts here, and that's the center tap winding. So we'll just mark it like this, so we know that this is the center tap. So this here should be the filament winding for the rectifier tube now, which would give us this last winding up here. So this is off, again. Right? I don't want to be ever touching this while anything is on. So now we'll take a look at the top here. Here we go. And 5.6 volts. So that is the rectifier winding. So this transformer looks like we have got a winner. So 5 volts here. Well, that's nice. You don't have to go rummaging through that. And it matches the other inductor. So hopefully the inductor is good too. We'll test that in a second. So this is 120 on this side. So that's what we've got. So we're going to rectify this and filter it, and that should go way up. And I'm thinking no load, we're going to probably be close to the capacitor's maximum that I'm going to be putting on there. So yeah, interesting. So again, as I mentioned before, there's drop across those rectifier tubes when they're loaded, all right? So you can kind of look at it like a peak detector when it isn't. So basically what's happening is it's going to just charge those caps right up to a peak. So no load, it's going to be really high. So I'm pretty sure that's going to be close to 450, those caps. So I'm going to bring this up slowly. Definitely bring it up slowly, because if it goes to 475, I have to stop at 450. All right, so that's pretty good. So what we're going to do now, obviously, is put a rectifier here. So we'll put our rectifier tube here, like so. So that would be our rectifier tube, and this would be the, of course, the center tap that's going to go to the ground off the filaments, or off of this supply here, and then this here, what I mean to say, is going to be running to the filaments. And here we go. And then we're going to have our inductor here and go off like so. So our first cap would go here. Fun stuff, we're already on our way. So let's test that inductor right now and carry this on here in just a moment. So I'll shut that off. As you can see, shut off. Move this out of the way, disconnect the primary, and get this out of the way. Nice. That's nice. I'm looking forward to working with that. Okay. Okay, so here we have an inductor of some sort. The reason I'm putting on this is so I don't scratch the bench. I notice when I have that gray mat here, it really causes the camera to, of course, overexpose my hands and everything. All right, so I'll grab the LCR meter here, and just an LCR meter that I've got laying on my bench, something that's easy and quick for you to see. I could use the Genrad or something like that, but hey, as long as it tells us what the inductance is, who cares, right? Right. Backlight. That's nice and easy to see, nice big display. Okay, what do you think we're going to be dealing with? Is it going to detect it first of all? If not, I might have to move the function over. I may have to do that now already. Okay, so here we go. So what we get. What are we dealing with? What are we dealing with? Oh, not bad. So we're dealing with 7.1 Henry, so that's probably at a higher frequency too. So let's see frequency here. 10 kilohertz. Let's go to 100 hertz. So 8.1 Henry. So it's probably spec'd out at like 10 Henrys or something at 60 cycles. So it's or close to. So Q of 9.2. Not bad. So we're dealing with something, you know, of course, this is going to be dealing with 120. Let's see, does it give us, oops. Let's see if it gives us 120 here. Let's try that over again. That's, yeah, it starts at 1 kilohertz. So frequency 100 hertz. Well, it does give us 120. So technically it would be at 120. So yeah, it's 8 Henrys. You can see that there, 8 Henrys. So not bad, not bad at all. So I think we're going to deal with this. I wonder what the DC resistance is. I'll just, these things aren't great with DC resistance, so let's just test this with a standard everyday meter that's going to give us DC resistance and get a quick and dirty reading here. What are we dealing with? It's going to see 151 ohms. That's not bad. Another thing you need to keep in mind, some of these meters won't read these. So they get really confused when you give them any type of DC resistance readings, especially for something that's got 8 or 10 Henrys or something like that. So keep that in mind. Some of these meters, it'll trick these meters. So this one here is just happens to be reading it, which I'm happy about. So this looks like it'll work, so we can carry on with our supply here. So basically what I need to do now is solder up some mock-up tube sockets and yeah, see what we can get out of this thing. So I'll get some parts and pieces ready here and warm up a soldering iron and start building, and you can watch me build this and see what we end up with. The first thing that I want to do is wire up the 5U4. So I'm going to mark this down on a piece of paper. Let's write this down right here. So we have the 2 plates. So the 2 plates are 4 and 6. So you can see PD2 and PD1. So I'll write 4 and 6 on the piece of paper here, right by the plates. That's all, 4 and 6. My scribbles here, it kind of looks like a 5, but it is a 6. And we want the filament pins, which are pin 2 and pin 8. So this will be 2 and 8, or vice versa. It doesn't really matter for our wiring purposes. So 2 and 8 written down on there. So now what I'm going to do is put a tube socket on that transformer, and I'm going to build this whole thing kind of, I guess you could say dead bug style, to what they call it nowadays, but this is going to be just put together on a mat because we're going to be doing some experimentation here before this actually goes on a chassis. I grabbed a junk ceramic socket out of my bin. So the first thing I want to do is attach the filaments. So that would be pin 2 and pin 8. So from the index, you count clockwise, there's 8 pins, so this is pin 8. And we have pin 2 right here. So I will connect these up. Bend them down a little bit, easier to see. So I'll just tack these on. Again, this is just, you know, kind of quick and dirty here for experimentation reasons. Just add a bit of solder to that. And that'll hold that nice and steady. There it is. And now I'll attach this. Will that even fit through there? Oh, it kind of does. Yeah, it does. So I will just tack this in and we should have filaments. Okay, so I've got that wired up. Next thing I want to do is attach the plate leads. So the plate leads are 4 and 6. So these are the plate leads. We need to go end to end for the plates. So we have 8, 7, 6. So we can bend that one off to the side like so. 5 and 4. Those are some pretty rigid pins. They don't want to bend very well, do they? I don't really need to be bending them. Probably shouldn't anyways, because if I'm going to use the socket for other experimentation, down the road, more bending equals more breaking. All right, that is one. Wait for that to solidify. And this is the other. Is that going to fit through there? It should. Will it? it does. Okay. Let's get that into a little comfortable area where it's not going to pop out while I'm soldering it. It's moving, it's trying. There we go. Okay, so now I've got the plate leads attached. So double check everything. So we got 1, 2, 3, 4, 5, 6. That's fine. And that's the filaments right there. No problems there. So this is the center tap for the B+. So what we can do is plug a rectifier tube into that. So what I'll do is I'll go look for a bunch of tubes. So maybe grab a bunch of regulators and stuff at the same time, get a box, and I'll plug one of them in. All right, box of pulls found. So we want this to look as old as possible. So let's use an old ST styled rectifier. Look at that, complete with antique dust. So let's plug that in. There it is. That's plugged in. So now we've got a rectifier tube in there, just like so. And that is a good thing. I'll move these out of the way. I also picked up some regulators and put regulators in here as well. So the next thing I need to do is attach the inductor to one of these. So that's going to be to one of the filament leads. Which lead is longer? Is this one longer? Will it work? It has a hook in it. Will it work okay? It will. I really should have a pair of pliers here so I can fix that bad solder. Again, you know, these transformers and inductors are just pulled, right? So let's see if I can make that stay. There we go. Okay, so that'll stay. So now we've got the inductor. So if we were to draw the inductor here, the inductor would be, I'll just draw this right outside a frame here and show you because I've got a mat here that won't allow me to draw on. So now I've added the inductor to one of the filament leads, so I can put a cap across here and a cap across here, and we can see what we get. So I'll go over to my cap bin. As you can see, this is very much just by the seat of my pants here, right? So grab a 22 and a 47 like I thought I may use. This is a 22. It is. So we can just tack that to the same area. Hopefully everything is going to stay here. Let's see. Hopefully this is all in view okay. It's going to want to pop off, I know that. This is going to want to go kerpop. Okay, so there's a 22 there. And on this side here, we will have a 47. Look at this, all real time. Let's add some solder to these leads. It's a brand new cap. Pre-tin everything here, just a little bit. Okay. This is about as, I guess this isn't like, you know, dead bug is you know, a solid state type of classification. What would this be, dead tube style? Hopefully not. You don't want any dead tubes. That 5U4 could be toast. I don't even know. Again, just pulled out of the box and right here. So okay, so now what I need is a jumper clip or something. Just a small little ground jumper clip. Very much, as I say, you know, fly by the seat of my pants. So I'll grab a bunch of jumper clips here. A whole bunch of jumper clips. So look for a really, really short one. Do I have a really, really short one? I do. Look at that. That's nice and short, eh? So the center tap was, this is the primary, that would be the center tap there. And grab onto that. And we'll attach it to here. So now what we've got set up is on here, really quick for testing purposes, I'll just draw this in again because of the gray mat, is we've got this going on. So we have our pi setup right here, 22, 47, both at 450. And there is no resistor on here to give us any type of voltage bleed off or anything like that. So this is going to be DC. So I'll put this here and put this here. I will attach the primary up again. This is true old ham operator style right here. This is the way it was done. So let's go here. I've got some light here. Hopefully you can see that. I'm trying to get rid of that glare. There's so much glare happening with all these lights. Okay, so we got on DC. So what I'm going to do is turn the variac down on the isolation transformer and current limited variac supply. Turn that on. And I'll bring that up a little bit and just watch this as that filament comes in. So it should come in nice and slow. As you can see, it's coming in nice and slow. So here we go. So it's the tube's lighting up. We do have emission. Hey, look at that, eh? Something's working here. Okay. DC's counting up fast. The variac's about a third of the way up. Look at that. Okay, let's turn it up some more. And that'll also heat the tube up, so this will come in a lot quicker. So we already have our 270. It's right up here. So we're about 3/4 of the way up. I think we're going to come in close to these caps rating. Okay, so now I'm going to advance this slowly from here. Look at this. Man, we're coming in close. That's right at the top. So talk about judging that transformer almost on the button. So the caps are rated at 450 and we're at 445. So I'll shut this down. And I will grab the safe capacitor discharger that I designed and released on Patreon quite some time ago. And you can see the two little LEDs here. So no matter which way you hook it up, one will light up here, and we'll drain this off nice and safe. Look at that. Nice and safe. Definitely don't want to be tackling 400 and some odd. So there we go. Now, because of dielectric absorption, there's no bleed off resistor, so this is probably going to climb up again. See that? The reason that it's climbing up isn't magic. That's just called dielectric absorption. So now you always have to remember this. This is another thing I've taught in my lessons, is whenever you're working on some of the larger amplifiers, some of the big old, say like a Sansui or say like an old Fisher, just for example, right? Macintosh. They have some really large caps in them, and you can discharge them, and you think they're discharged, and then you let them sit for a half an hour, and they'll climb up to a pretty high voltage again because of dielectric absorption. So a really good thing to do whenever you're working on an amplifier or anything like this is once you're done, you have to remember this though, is if they climb on their own, right? Pretty common in many devices, is you can put a shorting bar across the caps once they are discharged. Another thing that you always need to keep in mind with these caps is it's not safe to just short them to discharge them. So many people think that that's absolutely fine. That is incredibly hard on capacitors and incredibly wrong to do. So if a capacitor is charged up, you just don't go bridging it and then looking for a big spark. You got to remember that there's quite a bit of current there, and you're sourcing a lot of current to a jumper. right? So it damages the caps inside. So they need to be, bled off safely and in a manner that's not going to, source all the current, immediately. So again, you can see this is almost up to 5 volts again, right? That's enough to light these LEDs up nice and comfortable, right? Or one of them anyways, right? Watch. Oh, no, you didn't see it. Or maybe I didn't see it. But yeah, there you go. Like, I mean, it's just, and they'll climb again. Again, there's still, as you can see, it's climbing up. So a shorting bar can be put across these is absolutely fine, but you have to remember to remove it, because if you power up your amplifier again with a shorting bar across it, or power up anything with a shorting bar across it, I think shorting bar says pretty much everything, right? So this will stay relatively low now. And what I'll end up doing is, in the original design, I figured that we would put, say, a 100K resistor across that or something like that. So 100K resistor across 440 some odd volts, right? That's going to pull it down. So we'll say, what's it going to drag it down to? 420. So across 420, what's that going to be? 2 watts? About 2 watts continuous. So we'd want a 5 watt resistor, something like that. I don't have my calculator right here just to do that right now, but I'd say about 2 watts. So yeah, we'd want a 5 watt resistor or something like that in a worst case scenario. And I'll talk more about why I would choose 5 watts, even though it's pulled down in the actual supply down to what the radio is going to need. I'll explain all of that here in a bit as well. So I will look for a 5 watt 100K ohm resistor and put that across here, and we'll move on. All right, no glare. Go to ohms, 5 watts, 100K, or close to. 99.8, that's close enough. Okay, so what I'll do is I'll just tack that. Move this off here. I'll just tack that across here for now, because that's going to most likely stay there. It'd be interesting to see what this is going to come down to. It's probably not going to pull it down all that incredibly far, but it'll keep it a little further away, and it'll give it keep it a bit further away from the max of the caps, max voltage, and it will also pre-tin those there, and it'll also bleed the caps off. So I'll just tack that there for now, and put this into a different spot so I don't desolder the caps and then have to fight with that again. So I'll put that in a little bit different spot. There we go. Okay, so curiosity, let's see what it comes down to. I say 435. I don't know, I could be completely off the mark, but let's just see. Let's just try it out. Okay, so there we go. Everything's all hooked up. 100K across there. So, yeah. Okay, here we go. Can you see that? Let's see what we're going to try and get something with a little less glare on it. Okay, and power supply on. So it's pulling it down a bit, and it's keeping it away from the max. That's fine, and that'll discharge the caps now as well. So 433, we'll say. The movement that you see is the soldering iron turning on and off. So you'll see over here, it's not regulated. You can correlate, if I can back this out a bit, the numbers with the little dot going on and off. So when the dot comes on, the elements are coming on in the iron. And that's how it works with everything on this bench. So if I have a power supply that's unregulated, I've come across this so many times that these Hakko soldering irons, they pull a little bit of current, right? And you can see it's affecting this. So if I shut the iron off quickly, you'll see that it won't do that anymore. It stays at 433. There's a slight bit of movement, of course, because other things, but if I turn it back on again, right? And wait until it cycles again. See that? So anyways, something to keep in mind with unregulated supplies. So you're going to see that amount of movement. Another good reason to regulate this supply, right? So I'll shut this off. Let's see how fast that discharges. Isn't that nice? Look at that. That's coming right down. So that's discharging it really nice. So about 30 volts, 20 volts now. This is probably warm. Yeah, it's warm. That's a 5-watt resistor. So not bad. Not bad whatsoever. So that's nicely discharging everything here. So we have our setup here with a resistor across this right now. So I'll just draw that in off to the side. Again, due to our mat, I can't draw this in front of you. So we have the 100K resistor right there. So that's what we're dealing with right now. So we know that, with that resistor there, we're at 430. So that's at the point we're at right now. So we're at 430 right here. There's no load, no nothing except from that, little resistor across there. So it's nice. This will keep pulling this down so we don't have to deal with that dielectric absorption and these things charging up again, which is kind of nice. It's nice to know that the old ST style rectifier tube is working really well. Tube is nice and warm, not warm enough to hurt, but nice and warm, that's for sure. So these have got quite a bit of filament current. They draw quite a bit of current, so that's they get pretty toasty. And of course, it is a power tube, right? So dealing with that. Okay, so what are we doing next? We got to figure out what we're going to do for regulation. So technically, we need some form of shunt regulation system. So on the back side of this, if I can get you out far enough, maybe I can push the mat up. Again, really fly by the seat of my pants here with you. So I'm doing this all real time. So lots of fun. So we're at the other end of the inductor. So we have our inductor here, right? And we're at this point right here. We have our cap to ground here. Now, of course, this is the ground that we've created in the power supply. Again, this in the radio itself is actually isolated. So we're at this point right here, and we have that resistor also running down. So what we're going to need to do here is have a resistor like so, and this is going to have to run off to the radio because this is way too high, and it's still going to be way too high for the radio receiver itself. And then at this point where it runs to the radio, we need to add our regulators that come down here. So this here will be dealing with the radio's load, like so, and then this will run to ground as well. So this is going to run off to our radio, and that's what we're going to be dealing with. So this is a shunt regulation system. So we're going to need to fool with this resistor value here, so we can play with that value and see how close we come in. Now, I will get a whole bunch of things set up. I'll put the radio back on here, and we'll feed this to the radio without the shunt regulators and see what we get at the radio. So as I say, you can give these radios a dramatic amount of B+ and nothing's going to happen to them. So we'll start off with a relatively small value or larger value and move smaller. So I'll get that all set up and I'll be right back. Before I go about attaching the crude power supply into this radio receiver, I want to get the other power supply disconnected because I don't want to be back feeding the filaments on this transformers and then of course powering these transformers up through the filament winding. So what I'll do is I'll disconnect that, and I may as well just disconnect the B+ as I'm there as well. So that is the filament feed from the transformer down here, and the B+ going out would be this red lead right here. So it comes in here and then goes through the filters and then out this red lead right here. So we'll just disconnect this. We can tap the new supply into this red lead as well. And it's nice and long. Let's pull that out of there. Look at that. So we have a lead to attach to the power supply. So the center tach can be left hooked up because right now there's really nothing that's going to affect. So we can just leave that there. So those are the two leads that we needed to disconnect. Get that wire out of the way. And yes, we have our power supply here. So now what we need to do is, before we actually attach the regulation here, what we can do is just experiment with a resistor first to see where we get. And then, of course, if we put regulators across here, we're going to have to down this value because now we're not only feeding current to the radio, but we're also, the regulators are going to be pulling down on things. So this value will drop, which, of course, would up the voltage without the regulators. And then when you put the regulators in, everything will get pulled down again. So I'll explain that as I'm going along. It's, I guess I've just been doing this for too long. So anyways, what we need to do is get the filaments hooked up. So we know that the filaments are, one side is the chassis, right? So we know that we do have a ground here, so I'll just attach this to the chassis somewhere, maybe out of the way, like so. Nice big leads, and the filament windings were here, so I'll put this one here. And this one can go to the existing filament lead, which was this pin here, so I just put it right on there like so, right? So we can see if we've got any life in the actual filament zone on this radio here. Unfortunately, you cannot see the front of the radio, but yeah, and I can't turn this thing around because everything is all hooked up. And in the way, what I'll do is I'll just power this up briefly, and we'll see if we get any filament lighting going on here. So this is all yes, and this is open, we're fine, so we'll have to wait for that to discharge again. So here we go, that is on, and I will peek around the front of the radio, and yes, the dial lights are on. So we do have filaments going inside here. So they are glowing, so no problems there. So I'll shut this off, and I'll be a little bit impatient here and just discharge this cap a little quicker, rather than waiting for the resistor to bleed that off. There we go. Good enough. That is done. So now what we need to do is attach a resistor into here and see if we can actually bring some, B plus into this thing here. So what I'll do is I will attach the, we can go color coded, make things a little bit easier. So now remember the ground here is isolated and has to go to that center tap here. And that center tap was, and we can see that off to the side here. This is a little center tap here. That's where the center tap of the power supply is. So this has to run to this point. And remember that this goes through another inductor that's in this housing right here, in this transformer housing, to the actual chassis of this radio. So it lifts that up so that we get that negative 15 to 20 volts on the grid of the 6K6. So that should be to that ground there. Now we can't hook the B plus directly to this because, even at that, it's not going to pull it all the way down from 430 down to 200. There's no way it's going to do that. So we need to get a resistor of some form of speculation going in here. So I'll grab a resistor bin. You see this? And we'll start off with, say, something that we find that's common. So I would say a couple of K anyways. So it's 4,500 ohms. 1.6K. 1.8K. So let's put these off to the side. Try a couple of different ones. You're probably saying, Paul, why don't you just work this out? Why don't you try and just figure this out? Well, we have a lot of things at play here. What is this one? 2.7 ohms, well, that'd be low. We have a lot of things at play here. So the impedance of the supply, we have the drop across the rectifier, we have all of this stuff in play that we really don't know, like what's this actually supplying for current, right? So we can just experiment with some resistors, get a ballpark idea, and just work our way down. And that's easy. And that's the way that a lot of the radio manufacturers did a lot of things as well way back in the day. They just don't tell you that. They have design engineers going, okay, Joe, bring me the 1.5K resistor. Let's try that one, see how that works. No, we need to up the wattage a little bit. Isn't that a little bit, depending on the resistor, right? Oh, this particular style of resistor is rated at 5 watts, but it gets a lot hotter than that style of resistor rated at 5 watts. So give me that other one. And I'm telling you, this is the way they did things. So schools would have you believe that everything is done on paper and math. No, it's not. It never has been. In fact, that's pretty laughable. So anyways, let's go here. 4,500 ohms, whatever. Let's try this first. See what it does. So put 4,500 ohms here, and then we're going to go to the B+. So that was this wire right here. So what we'll do is a nice little short lead right here. We'll put this on here. and run this over to the 4500 ohms and see how much that pulls down. So we'll see what the radio gets pulled down to. Now that's going to draw the supply down. We're going to have this soggy rectifier here doing its thing. We'll move this. Is that on DC? It is. And we'll see what goes on here. Put that to the chassis. So now we're not measuring to the center tap, right? Because we have the drop. So we're looking for a target of about what, 210, something like that. So that should be roughly what's going on here. So put that there, and let's see what happens. All right, radio is on. Obviously it is because the filaments were glowing. So we can measure this at the radio now. So let's see what we get here. Turn this on. And so now this is going to go really high, right? Because remember, the tubes aren't warm in the radio. Once they come into emission, it's going to drag that right down. And as you can see, the tubes are warming up, and we're coming right down. And we're going way below our target, aren't we? We're back to where we were before, roughly, right? Was it 170? Even lower. So 4.5K is a little bit, a little light. So we're at 159. Now, so you see how much that dragged down, right? And that's because the filaments are warm now. So when they come into emission, about 13 seconds or so, and they come into emission. So I'll shut everything off, and as you can see, we're pulling things down quickly because the radio is still in emission. The filaments are hot. They slowly cool off, so it drags all the caps down with it pretty quick as well. So we had that at, that was 4,500 ohms. So what we can do is, let's try this 1.6K just for the fun of it, because nothing's going to get hurt. It's not how it works with vacuum tube gear. Vacuum tube gear is pretty resilient. So here we go. We're way up here. That's our overshoot again. And it does this in normal radios too, just in case you're thinking like anytime you have a directly heated rectifier like that. Hey, look, we're coming in pretty close, aren't we? So this is going to be high still, because it should read this. It should read this at the between this and ground here. So we need our negative 15 volts. So this should be 210. So we're about 225. So if I grab another meter here, let's see. Something else I can just grab and hook up. Hopefully I've got leads over here that I can display this with. Okay. So if I was to say hook this up to read the ground, right? We still have that negative 15 volts that we're going to need. So it's probably going to be high because all the rest of the voltage, the leads are just tangled here. So pardon me. Again, fly by the seat of my pants here. I'm just doing this real time with you. So trying not to edit anything that doesn't need to be edited out here. So, okay, so we got DC here. So we're what, 221? It's probably going to be getting hardly warm at all. So let's see here, from the chassis to here. So we have negative voltage, right? Because of the inductor. So put that there, and here. Yes, we have negative 16 volts, right? And that's because of that inductor. Right, so that's high. So we're probably going to be close to negative 15 volts when this is actually right. So I grabbed a 1.6 and a 1.8. So let's just try it out. So I'll shut this off. Let that settle off here again. So this is about 1.8K. So this will probably bring us in very close. And look at that. Those are the first couple of resistors we just tried. Sorry about the noise in the mic there. Yeah, let's see. Move that out of the way. That's getting pretty toasty. Not toasty enough not to hold, so probably would be okay. Let's try this. Okay. All right, so we should probably come in pretty close, because that's going to drop it down. We're a couple hundred ohms up now. So tubes need to come into emission here again. Hopefully you can see all this. I don't know if I can get any closer without losing some of the cameras here. That's still a little bit high. So it might actually be, say, that's 215. That's not bad, right? So, say 2K ohms would probably get us right about where we need to be. maybe 2.1 k ohms. Let's see if I got anything in here that would be close to that. Just trifle through the box over here. 214, 213, as it's warming up, it is coming down a bit. Now keep in mind there's some drop across that variac circuit as well. It's probably about 118 coming out of that variac. So when I plug this into a real 120 line, that'd probably go right back up again. So let's see if I can show you what I'm doing here. So I'll just move this over. You see over here. All right. So we want something about 2K, right? I don't know if I've got anything in here that's going to be exactly on 2K. We can add to that resistor a 1.8. So a couple hundred ohms. There's 220 there. So that'd be a little over 2K if I put this in series with that one. So we can grab this one and maybe one that's even a few hundred ohms more. What's that? 130. That's another 220. So yeah, there we go. It's just 2.7. It'd be nice if I just had a 2K resistor. Another 220. It's kind of bent. Whatever. Same one. What is this? 3.3 ohms. That's a little low, isn't it? 2.7 ohms. Okay, so let's just go with this. And I get that out of the way. Off to the side here, and let's just look back over here again. Okay, so let's put another one in series with this. I have another short jumper of some sort here. Well, short enough, I guess. Not short enough. Okay, so let's add another 220 ohms here. So we're going to be up about 2K, or close to. Okay. What do you think? You're coming closer? Let's see. Here we go. Hopefully you can see that. Okay. That helped? No, just makes it worse, doesn't it? Hey, look at that. 210. Right at 210, 209. So we're coming in pretty close right now. So if we didn't want to have any regulation, you can see how much that's moving around right now. We're moving around a volt and a little over a volt, right? 207, 208. That's just with the soldering iron cycling. So if I shut the iron off, you see how close we get there. So now we're just moving in the millivolts without the soldering iron going on. At least it's stable at 208. But we need the soldering iron going, so I gotta turn that back on again. So, and it'll pull it down here in a moment. There we go, 207 again. So, yeah, we're coming in very close. So maybe 100 and some odd ohms, but this is fine. If we wanted an unregulated supply, that's close. And let's see if we're close to our negative 15. So that would tell us that if we did use a 225 volt regulator, we'd be spot on, wouldn't we, at 210? And see, look at that. Look at that, 15.3. So we're really close to our target here. So 207, so if I didn't want a regulated supply, I could use a 2K resistor and, or say 1.9, whatever, but 2K is close enough. And that would bring us in with just what we have here. And we could actually even listen to the speaker and see how much ripple we have. Well, let's see how much ripple we have right now. With just, let's see, what can I do here? I'll go to AC. Just see if we can measure this here quickly. Quick and dirty. Nothing on a scope or anything like that. Should be nice and low. Hopefully you can see this here. Okay. So we can go from here, which is our ground, to the supply, which is going to be running into this point right here. We got AC going on here, DC going on here, so we got to... This isn't reading very well. Hold on, let me get that in there. Obviously I have a cap going on in here. It's getting confused. This little meter doesn't know what it's doing. So let's try going with this one here. So what I'll do is I will just, because there's not going to be that type of ripple on there. There's absolutely no way that ripple's going to be there. So that little meter's being confused. So what I'm going to do is shut this off and let that discharge real quick. Move this to AC volts and then turn this back on again and see what we got for AC volts. That's a very noisy bike. So we're doing pretty good. Look at that. About 0.1 of a volt, and that's not with the other reactor in there as well. That's right across this supply here, so it's 0.05 volts, to 0.1 volt. That's absolutely fine. That's going to be a very silent supply. So those caps are working out very well in there. You know what? Let's grab a speaker here. What I'll do is I'll grab a speaker and I'm going to grab an impedance matching transformer because these are higher impedance, about 300 ohms or so. And we'll put that through an impedance matching transformer down to a regular 8 ohm speaker, and let's listen to it and see if we can hear any hum in the actual speaker. Okay, I've got a speaker attached through an impedance matching transformer. I'll also show you a little trick throughout the series of this receiver, how you can get away from using a dedicated impedance matching transformer in cases like this as well. Again, a little bit of old ham operator knowledge that really isn't talked about all that much. So that'll be coming up in this series as well. So let's see if we have any noise going on here. So I'll turn this on. So we'll let everything warm up. Oh, I heard a little bit of noise there. I can't hear anything. Wow, that is silent. I'll just see if there's any... Oh, it's trying to receive. I'll touch one of the antenna jacks here. So it is... You can hear that. It's trying to receive with no antenna. So I'll turn this right down again. If we're going to hear any hum, we're going to hear it with the volume down. Hardly anything there. Is a little bit of noise in there, but that could be attributed to having this whole thing open like this. And it would make sense too, because that's a lot of filtering. Yeah, that is. Can you hear anything? Very slight. So probably just, again, residual, having everything open here. So a little bit of buzz in there, but that really doesn't sound like AC hum. So we're doing very well. So definitely enough filtering in the supply here. And that is, like, from this point here, silent. You wouldn't even know this radio is on. There's nothing here, zero here. So very good filtering. So that'll be very nice with a headset. Say you wanted to use a headset with something like this. That would be very, very nice. So we'll do all that testing in the end as well. So we're doing pretty good. This is with no regulation. We're coming in very close. So technically the supply that's in there right now should be like this. So it should have been like this, not at 270. It should be around 210. So if we didn't want to use regulation and we wanted it just to be a very simple supply, we could take what we have here and basically put it into a chassis, and we would have just a standard supply for this radio receiver. But that's not good enough for us. We want to have regulation. So this movement that you see here in the volts, we want to take that movement into the millivolts with the soldering iron moving. So we can see movement in the millivolts, but not in the volts. Okay, so I'll shut this off and let that go down. So we've got pretty much nothing there. So what I'm going to do is I'm going to grab the two regulators and get a little bit of some stuff just preset up here, because I'm just going to be hooking clip leads onto leads of the regulator tubes and stuff like that. I'll get that all hooked up, and we'll make a shunt regulation system for this thing and see how well it performs. I'll be right back. What we want to do is attach two regulator tubes in series. So we want to attach a 0A3, which is a 75 volt regulator, in line with in series with a 0D3, which is a 150 volt regulator. So they operate at a maximum of about 40 milliamps, but when they start up, they can deal with 100 milliamps for a short period of time, basically the warm-up period of the tube, or a little longer. So the diagram for those tubes is 4AJ, which is down here. Now, there's a bunch of things about regulator tubes that a lot of people don't know. First of all, you'll see that there's a jumper. See where it says JPR and JPR? So when these are wired into circuits by manufacturers, what they do is they use the jumper inside of the tube to disconnect internal circuitry inside the power supply, just in case a regulator tube is pulled out. So say in a case where you have a pass element or something, say a 6AS7 or 6080 or something like that. Well, here we go, right? 6AS7, 6080, right? So a pass element, or what they call back in the day series, voltage regulator tubes. What ends up happening is if you pull the reference out in a circuit that uses a pass element, what'll end up happening is the voltage will skyrocket and it won't come down. So by feeding portions of the circuit in there through a jumper, so say if you pull this tube out, it'll disconnect the output of the 6AS7 from the load. All right, so it'll actually completely disconnect it because you're removing the jumper. It protects the circuitry. So that's basically what this is. So if a tube gets pulled out or it's missing, the power supply won't work at all. And that's the reason they put a jumper in here. So you can use the jumper for many different things. Some people will use it to disconnect filaments. Some people will use it to, even disconnect an AC supply so that the entire thing won't power up if one of the references or one of the regulators, a shunt regulator, or in this case, again, this would be in series, but two series shunt regulators are missing. So you could hook up the jumper of this one to the jumper of the other tube and run them both. So if either one is pulled out, the circuit will not work. And in the end design, when this is put into an actual case or project box or on a chassis of some sort, that will happen in this design as well. And I'll explain that as I'm going along. That's just a safety precaution. They gave you that option. The dot inside the tube means that it's a gas-filled tube. All right, so whenever you see a tube with a dot, that means there's a gas in it. You'll see a regular tube like this does not have a dot inside the envelope. That means that this is not a gas-filled tube. This just has a vacuum in it. So we know that pin 5 is the plate, and we know pin 2 is the cathode, and we have to put two of them in series. Okay, so as you can see here, I'll back this out. As you can see, I've got two of them attached in series. So pin 5 goes to pin 2. All right, so you see pin 2 here will run to the center tap. And so pin 2 to pin 5 to pin 2, and then pin 5 will run off to the B+ supply. So we'll have two of these in series. All right, easier than wiring up a socket right now and having to do that. So let's put these right down here like so. And when these glow, one should be a purpley color or mauve or whatever, and the other one should be orange because one is has a different gas inside it. All right. So in order to power these up, in order to make them act like their shunt regulator selves, we need to attach one to the center tap here, which is a ground. Okay. And the other one will have to go right over to B+. Now, keep in mind here that the resistance that we have here is now going to be pulled down by two regulator tubes, and it's also going to be pulled down by the radio. So we're going to need to down these resistance values. All right, so I would down it by half actually, but we'll try this all out and make sure that I'm on the mark. So the whole idea is to have these regulator tubes come in and operate around 25 milliamps, something like that. Maybe even 30. So between 20 and 30 milliamps is fine. I want about a 10 milliamp safe zone when they're operating, and that way these tubes will last a long time. So we'll experience that as we go. So what I'll do is I'll move this over here like so you can take a look at the actual tubes as they're doing this. They will come in, but they won't be at their brightness that they should be. So nice if I had something here I could cover this with. Okay, I'll turn everything on here. You can see the voltage here come up and all that. Here we go. So when the rectifier, you see they pop into action. So this is the 0A3 and this is the 0D3. Now they're brighter on camera than they are in actual right here in reality. But that's because the camera is sensitive to the glow discharge. Now you can see them dimming out. You can see the voltage is being pulled down by the radio and by these regulators, and you're going to see They may even pop out of service. Oh, you see, there they go, right? So now what's happening is they're actually kind of below their firing voltage. This one here still may be in just a little bit because I do see it pulling it down here a little. So what happens is the voltage has to exceed their operating voltage to make them start, like you saw, right? So they kind of pop into action, but when the tubes start glowing inside the radio, what ends up happening is they're drawing current. So now not only do we have the radio pulling down, but we also have these things trying to pull down as well. And as you can see, there's a little bit of glow still trying to happen in there, right? So it's still trying to do its thing, but it's not doing very well at all. So you can see that little thing in there, which just helps it strike, a little thing that's sticking out in there. So strike or ionize, whatever you want to call it. So anyways, what I'll do is I'll shut this down. And what we want to do is drop that resistance in half. So we're about 2K, and we'll see what happens. So what I'm going to do is grab a one. Actually, these here should probably do the trick. It says 470 ohms. So I'll just put 2 of them in series and see how that works. So what we're going to do is get rid of all of this in here, right? And take that from 2K down to, well, 470, and 470 is just under 1K, but we'll see here. So these haven't even been tried yet. Fresh out of the bag. Okay. What I'll do is I'll just tack these together. Again, real time here. No fooling around here. So I'll just put some solder on those. Brand new resistors. I might even just use these if this works out. So I have a feeling it probably will. So you're probably saying, how do you know that? Well, now that I'm seeing everything happen the way it is happening here, I'm starting to see a pattern. And of course, that pattern is equaling what I'm coming up with here. So I'll just let that solidify for a moment. There we go. Put that back. Okay, so let's get rid of this. And so we got this here. And this here. That's nice and warm. Okay, so we want to go from here to here only. There to here. Okay, so we have our 2. So we have about 1K worth right there. And we want to attach our, get this out of here. We still have our regulators attached, do we? We do. So get that out of there, get all the confusion out of the way. Put this out of here, and this out of here, and nothing's touching. So there we go. So let's see what we got going on now. See if we have any more luck with a lower value. I have a feeling we'll probably be just fine. So, okay, everything is good. We're good here. We are. Okay, radio on. There we go. See those pop in. As soon as these come on, you know that the rectifier tube is into emission. That's how quickly it comes in, about 3 seconds. So now that's because it's going to be way over current right now. And then as the radio comes in, it will bring these into spec. And we'll see how close we are. Now these have to warm up for a moment. There we go, we're at 209. And again, this is not, 208, 209, 208. So not too bad, but again, this is in that variac supply. So we're only moving a matter of, because you can see it's right on the border here, we're only moving a matter of about 209, 2088. So we're moving about, what, 30 millivolts? So even though you're seeing this move right now, we're only moving about 30 millivolts here, right? Because we're almost 0 here. Right, see, 6, 8, yeah. So about, you know, between 20 and 30 millivolts is our movement. So now, again, the variac supply that I'm running right now at the top here, over on the top, is down about 1.5 probably about 118, something like that is where it normally operates at. That's right at the top of the variac. So what I'm going to do is I'm just going to move this, I'll unplug this and just plug this into an actual, just unplug that and plug it into a regular outlet where we actually have about 121 and see what we get. Okay, so here we are, back plugged in again. Let everything warm up. That is almost spot on, isn't it? So we're at basically 210, 211. And as everything warms up, things will come down. So we're 211, 210.8. Yeah, 210.8 to 211. Yep, 210.8. So we're 20 millivolts, roughly. So that's a whole lot better than moving around over a volt, right? Or around a volt back then. So we're now in the millivolts. So we're, you know, safely we'll say 20 to 30 millivolts of movement, and that's with a soldering iron on. So if I shut the iron off, let's see how stable this is. Look at that. Now keep in mind that everything's cold. This all needs to warm up too, and when it's on a chassis, the standard warm up for one of these radio receivers is about 15 minutes, maybe half an hour, and then everything will really stabilize. Like look at right now, what are we out? You know, out to the second digit there. And that's without having that thing draw current at the bench. So keep in mind there's a lot of other things on the bench right now. That is pretty good. So we're dealing with 211. So we should have our 15 volts too. So I'll just turn this on. We also need to check the current that these things are drawing as well. We don't want to make sure that they're not dealing with over 40 milliamps. So let's actually do that right now. So I'll shut this all down. Just make sure that everything is good here. So I'll unplug this down here. Unplug that. And let's get this in line here. So we'll go over to 40 milliamps here. So the milliamps, right? Yeah, those milliamps there. Click this in here. This will just stay on for a moment. Okay, so we'll go from the power. Actually, we can just go from the power supply to this. Let's just do this. And then from here, actually no, we're measuring the current of just. We just want to measure the current of the regulator itself. So let's just measure the regulation current here and make sure that's all okay. So we'll do this to here. Actually, if we want to see it the right way, we'll go to this. It comes from the regulator, so you don't get a negative reading. Doesn't really matter, it doesn't read either way. So we'll put this on here like so. Okay, so now we should see in the milliamps here. So now when I power this up, I should expect to see, I'll just put this back into the variac supply over here, shut that down, reach over here, put this back into the variac supply. Okay, so now what I'm expecting to see is this shoot up over 40, right? Because it should, right, until the radio starts to pull current, and then we need to be within a zone. So I would say between 20 and 30 milliamps would be okay. If it is, then we can probably stick with this. And if it's a little low or high, I can tweak the values here. So I'll turn this on. Okay, so when these pop in, we'll see that. See, and now we're up to about 75 milliamps. That's way too much for these tubes. Okay. Now, as this comes down and the radio starts to pull current, this needs to come into a comfortable zone. And look at this, where we're starting to settle off. Look at that. So we're right in our zone. So I can leave these resistors. So I can actually build a power supply with those resistors, and I will. So now that's 209. So at 210, say plugged into a regular outlet again. So we're probably going to be dealing with about, I would say maybe 30 milliamps. Right in the same zone. It's going to be pretty much the same rate. So that's just absolutely perfect. So we have a perfect power supply right now, and lots of stability. So you can see them doing the regulation, right? And it's keeping it nice and stable up here. That's nice. That's really working well. That is very good regulation for a radio. Keep in mind that these things had dynamotors in them, and you know, the power supplies that were, I guess you could say, suggested for these radios are no regulation whatsoever, nothing. So it's just as it was before. Remember how we had the resistors in just this? And I said you could just put that in and kind of leave it at that. So now we're starting to deal with some pretty good stability. So this would be an excellent CW or single sideband listening radio with this. And of course, with the product detector in there, this would be very comfortable listening. You wouldn't basically hear, after it's warmed up, you'd hear pretty much no pitch change or any type of a tone change. That is very, very good. You know, the fact that we're out here, normally it's in here where it's moving around, right? We're out to here, right? So that's very, very good. So now if I disconnect this here, shut this down, and then again, plug this into just a regular outlet. So I'll move over to the other side here again. Plug that into a regular outlet there. So we'll let this all settle off again. That is so close. So once things warm up, you know, we're going to be dealing with about 30 milliamps. So we're still 10 milliamps away from our max, and these can run at 40. So the fact that it is at 30, these tubes will last a nice long time, and they're actually doing some pretty good regulation. They're pulling. Now, here's the thing. So this is always kind of interesting. So now when I remove the regulators, because we've dropped the resistance of this down, the voltage should jump way up, right? The voltage should go way up. So what I'll do is I will just disconnect one of the leads from the current meter here, and that'll disconnect these regulators from the circuit, and you'll see this go up. So it should, you know, not go up incredibly much. I would maybe 60 volts, 50 volts, something like that I would think, but it's going to jump up. So let's see here. So there's no regulators. So there you go. Look at that. So we're at 247. So the radio is seeing 247 right now without the regulators, and then of course with the regulators on, it pulls it back down. So you can see they're doing their job. These two tubes here are doing their job quite nicely. Now you can get much, much better regulation out of these tubes. This is just a shunt regulation system. This is very crude, okay? If you wanted to use one of these particular tubes as a reference for like an error amplifier type circuit with a pass element using a couple more vacuum tubes, say a 12AX7, and say a 6AS7 as a control element for a tube for the entire radio, this wouldn't move at all. So there would be zip for movement whatsoever. We'd be way out over here in the digits, right? Way past the decimal there. So we would be absolutely fine at that point. But for what we're dealing with this radio receiver, this is so, I guess you could say, overkill for the application that this is absolutely fine. We really don't need to go any deeper than this. So, and any more complex of a circuit at that. And these resistors here are, you know, way overrated, you know, so like, I mean, those are just going to get, you know, I guess you could say warm to hot. We're right within our target zone, 31 mils, and basically 210, you know, 209.8587. So look at how good that is. That's absolutely perfect. So we have success. I'll just, actually, the Variac, I was going to reach and shut off the Variac, but it's not plugged into that. So I'll just unplug this here. So we have success. So now the next thing that needs to be done is this needs to be put into or onto a chassis. And I think, honestly, this would look really good on an open chassis right beside the radio receiver. So basically you could see the tubes glowing and you'll see the transformers and everything, maybe a jewel light on the front. So what I'm going to do is I'm going to look for a project box of some sort. I have a whole bunch of Hammond boxes I've got kicking around here for different uses. And I'll probably put this all on top of one of those nice Hammond cast type boxes with the tubes. So I'm thinking maybe the rectifier in the center and the 2 regulators off to each side of it. So it would be kind of like, I guess if you were to look at it, I really don't want to handle that tube because it's hot. So I'll grab another one out of my junk box here. It's a 5R4. So basically it would look like, you know, on the chassis, something like that, you know, with the rectifier in the center and the 2 regulators off to each side. Maybe have the 2 transformers behind it. Let me know your thoughts in the comments below, and in the next video we'll put this all onto a chassis, and we'll go through the entire process. I'll paint the chassis, drill the holes, put all of this in, mount the circuitry, and you'll get to see all of that as well. So yeah, if you would like to see this on an open chassis, let me know. I could put it all into a box, but it's going to hide it. You know, so, and these look so nice when they're glowing, especially in the dark, or if you're in a nice dim radio room, you see the nice orange glow of the 0A3, and you see the nice kind of a mauve purpley glow of the 0D3, and you'll see the rectifier filaments glowing, you know, in the actual rectifier tube over here. This is a 5R4, looks like. So, looks like this one's been pretty hot too. Look at the discoloration in the plate there. So somebody has had shorted capacitors in some device. So this one's probably got some time on it. But anyways, just another one in the boxer. So yeah, I think that'll all look really good. So and paint up the transformers, maybe paint up the transformer bells, and make everything just look very, very nice. We want it to look like a brand new power supply right next to this radio receiver. Again, this is going to be, you know, compared to all the other ones. So we have to give this one a fighting chance. So anyways, there you go. That's what'll be involved in the next video. So stay tuned. If you haven't subscribed, definitely make sure you do that, and you'll get to see the entire process of this being put into a chassis or a box. Hope you enjoyed this video. If you are enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be more videos like this coming in the very near future with a lot more electronics content, new and old. This channel is all about electronics. So if you're into electronics, this is the place that you're going to want to be. Don't forget to subscribe and tap the bell symbol so you're notified as soon as I post a brand new video. If you're interested in learning more about my thought process and more about electronics in general, and learn about it in a very different and a very effective way, so a way that will help you learn electronics faster than pretty much anywhere else, you're definitely going to want to check out my ongoing electronics course on Patreon. You'll learn a lot more about my thought process there. There are lots of projects for you to build, and basically just get your hands dirty with electronics. It's the best way to learn. Lots and lots of content there. About 200 videos on Patreon now, are very, very close to. So check it out. I'll put the link just below the video's description under the Show More tab, and I'll pin the link at the top of the comment section. So click on one of those links and it'll take you right there, and you can check out everything that I'm doing behind the scenes here and the stuff that you don't see here on my regular YouTube channel. All right, until next time, take care. Bye for now.